What happens if a signal is sampled too slowly? Surprisingly, the result is not simply a lower quality version of the original signal. Instead, the signal can appear to change into an entirely different frequency. This phenomenon is called aliasing, and it is one of the most important concepts in digital signal processing and RF engineering. In the previous lesson, we learned that a continuous signal can be converted into digital samples if the sampling rate is sufficiently high. The sampling theorem tells us that the sampling frequency must be at least twice the highest frequency contained in the signal. This condition ensures that the original waveform can be reconstructed accurately. However, engineers do not always have the luxury of sampling at arbitrarily high rates. Analog to digital converters have speed limitations, storage systems have finite capacity, and communication systems often operate under strict bandwidth and processing constraints. As a result, there is always pressure to use the lowest practical sampling rate. The challenge arises when the sampling frequency falls below the required Nyquist rate. Instead of simply losing some detail, the signal can become fundamentally misrepresented. Frequencies that never existed in the original signal can appear in the sampled data, leading to serious errors in analysis and communication systems. Aliasing is the phenomenon that occurs when a signal is sampled at a rate lower than twice its highest frequency component. Under these conditions, high-frequency components become indistinguishable from lower-frequency components in the sampled data. The sampled system essentially becomes confused about the true frequency of the signal. Because there are not enough samples to uniquely identify the waveform, different continuous time signals can produce exactly the same set of sampled values. The digital system therefore interprets the signal incorrectly. The false frequencies that appear in the sampled representation are called aliases. These aliases are not actually present in the original signal, but are mathematical artifacts created by insufficient sampling. Once aliasing occurs, the original information is generally impossible to recover from the sampled data alone. Intuitively, aliasing can be compared to the famous wagon wheel effect seen in movies. Sometimes, a wheel rotating forward appears to slow down, stop, or even rotate backward. The wheel is not actually changing its motion. Instead, the camera captures frames too slowly to represent the true rotation accurately. Physically, consider a sinusoidal signal with a frequency of 8 kHz. If it is sampled at 12 kHz, the sampling frequency is below the required Nyquist rate of 16 kHz. The sampled points no longer uniquely represent the original waveform. As a result, the digital system may interpret the signal as a completely different lower frequency. Mathematically, sampling creates repeated copies of the signal spectrum at intervals equal to the sampling frequency. When the sampling rate is too low, these spectral copies overlap. This overlap causes frequency components to fold into lower frequency regions, producing the aliases observed in the sampled signal. Aliasing is a critical concern in RF engineering because modern communication systems rely heavily on digital signal processing. Before a received signal can be processed digitally, it must pass through an analog-to-digital converter. If the sampling rate is insufficient, valuable information can be corrupted before processing even begins. In software-defined radios, radar systems, satellite receivers, and wireless communication equipment, engineers carefully select sampling frequencies to prevent spectral overlap. Anti-aliasing filters are often placed before the ADC to remove high-frequency components that could create aliases during sampling. At the system level, aliasing can lead to incorrect frequency measurements, distorted demodulation, reduced receiver sensitivity, and increased communication errors. Understanding aliasing is therefore essential for designing reliable RF and signal processing systems. Fortunately, aliasing can often be prevented through proper system design. The first line of defense is ensuring that the sampling frequency satisfies the Nyquist criterion. Sampling above twice the highest signal frequency greatly reduces the risk of spectral overlap. Another important technique is the use of anti-aliasing filters. These analog filters remove frequency components that exceed the allowable bandwidth before sampling occurs. By limiting the signal spectrum, engineers ensure that unwanted frequencies cannot fold into the desired frequency range. Aliasing matters because it represents irreversible information loss. Unlike many other signal impairments, aliasing cannot usually be corrected after sampling has occurred. Once false frequencies are introduced into the sampled data, distinguishing them from genuine signal content becomes extremely difficult or impossible. In this lesson, we learned that aliasing occurs when a signal is sampled below the Nyquist rate, causing high-frequency components to appear as false lower frequencies. We also saw how insufficient sampling leads to spectral overlap, and why anti-aliasing filters are essential in practical digital communication systems. In the next lesson, we will explore signal reconstruction and discover how engineers recover continuous time signals from discrete digital samples. If you found this useful, like the video, subscribe, and follow for the next lesson.